how the real part of N2 depends on the angle of incidence. And in each case, we just read this off at the peak of these curves here. So, so this was all in what we call the perturbative limit, where it's just N2 times I. And in a material that's this nonlinear, we had to actually work pretty hard to keep our intensities low enough that we were in the perturbative limit. So, but why stay in the perturbative limit when you can go outside the perturbative limit? So what we did now is went to much, much higher intensities. And at these much higher intensities, we got some very unusual results. So here is the absorption of the material. Hey, absorption goes down, not so bad. Here is the transmission through the material. It correspondingly goes up. But what is really, really strange is that the reflection also goes down. This is the Fresnel reflection. Now, in nonlinear optics, you rarely are in a situation where you've changed the refractive index by such a large amount that the Fresnel reflection coefficient gets modified, but that's exactly what was going on here. So, so knowing these three curves, you can just do a little numerical calculation. You propagate a beam of light through this, and you can back out the real part of the refractive index and the imaginary part of the refractive index, and you see that the real part of the refractive index increases from 0.4 to something like 1.1 as you increase the intensity. Of course, we said epsilon near zero, not really at zero. Yes?
Is this for a normal or on the angle? 30 degree angle.
I cannot count on Zahir always being in the room. That will, that will get added to this curve so that in the future I have this with me. Okay, so epsilon near zero. So the refractive index was much less than 1, but it wasn't really 0 because the imaginary part of the dielectric constant, as you all well know, makes a contribution to the refractive index. So what are the implications? And then we measure the response time. And using standard pump probe measurement, we find that the rise time is no longer than 200 femtoseconds, recovery, fall time, 360 seconds. So implications. First, this type of response time strongly suggests that the origin of the response is a hot electron effect, meaning that you've heated the conduction band electrons. You haven't heated the lattice. If you heat the lattice, you'll have a response time of milliseconds. These are just the electrons that are in the conduction band. You heat them up, that changes, but they have to obey Fermi-Dirac statistics. So heating them up changes dramatically the optical properties of the material. This will support switching speeds as large as 1.5 terahertz. So what are the implications of this work? Well, the N2 value is very large, but conceptually, this tells us that the usual power series description of nonlinear optics is not adequate for describing this material. So this would be so much fun. We can have fun reformulating the laws of nonlinear optics. And classroom students maybe don't know this, but every night after lecture I go home and I say, now how would this be different if I set n equal to 0 in that equation? So, I mean, I'm having fun. So here's some possible new effects. Wave guiding outside the weakly guiding regime. You know, when we do fibers, for example, we always assume that there's a very small difference between the core and the cladding. Efficient all-optical switching. No need for phase matching. Well, if n is equal to 0, k is equal to 0. So, I mean, the phase matching is automatic in many circumstances. I didn't put this here, but radiative processes. You know, the Einstein A coefficient depends on the refractive index of the material. So there will be profound modifications of how light interacts with matter in an epsilon near 0 material. And I think that this is a perfect time to stop. because there's plenty of time in the future. So let me, actually, let me just stop here. And I thank you very much.
Thank you very much for a very, very beautiful talk. We have time for a few questions. Yes, please.
So you started with this about using materials, finding motivation that you can do switching with single photons. So are you close to achieve this?
No. Of course, that's the motivation for that's what we're trying to do. That's where we're heading. So well, if there were no loss, but of course that's always true. If there's no loss, you propagate for an infinitely large distance, and it always works. So we've picked up a factor of 100 in N2. And I think that's enough that it gets interesting in terms of single photon switching. But the amount of background loss that we have means we have to have very short propagation distances. In fact, a detractor might, at this point, say, you know, we heard what you said, but that's very, very self-congratulatory. It's really that the light doesn't propagate far enough that you have to worry about phase mismatch, which is also true. Which is also true. But that's where the work is heading. And there's a huge materials science aspect to the next steps of this process. We need to find other ENZ materials in which the loss is much lower. That's what we're working on. We have some ideas.
I have a question that relates to the last statement. What about ENZ affecting metal? So I would guess that the loss is really high there, but is that going to
Well, the ENZ wavelength is in the ultraviolet,
yeah.
and I don't have any ultraviolet lasers.
Okay, so it's just the wrong way.
Well, but of course, that's the engineer in me speaking. The physicist says, well, yeah, if there's interesting physics to be had there, why not do it? And of course, Paul Corkum is here, who can even generate coherent soft X-rays.
Right.
I have not given that thought sufficient attention. I mean, it has occurred to me, of course. How the scaling works, I don't know. Zahir Orad and I work very hard. I suspect that before bedtime tonight, there will be a flurry of emails among the three of us.
Okay. Well,
Yeah.
send one my way.
Yeah, no, yeah. Once, we'll do you a favor, and we'll send it once we have it figured out.
Any more questions?
Yes.
The entangled photon, when you detect all detect, how can you kind of time in them at almost the exact time to detect the different, the two photons
Right.
at the same time?
Sure. Okay. This was the pedagogical talk, of course. So you measure it here, and you have to infer what the emission time was inside the crystal. Well, you do it. I mean, they're correlation methods. They're correlation methods. Picoharp, time harps. You get picosecond time resolution to your ability to determine how simultaneous two events are. But I guess the point is that you say that's not. You could say that's not what I mean by instantaneous. But the inverse of a picosecond is something very broad in the frequency domain. So if it was a conceptual point that you want to make, that when you determine the emission time of this photon, you cannot measure the spectrum of the other photon, that's still a clean measurement that you can make.
Yes.
I'm very interested in this work on the ITO. So ITO has a very large amplitude at 1
It does, yeah. It has a pretty large N2 to begin with.
Right. So as an engineer, obviously,
So let me, I will always filter the question through what part of it I can answer. So the ITO is non-stoichiometric. The relative, it's indium oxide mixed with tin oxide, and depending on the exact mixture, that changes the E and Z wavelength. The samples that we bought commercially, the one that worked best, happened to work at 1.24 microns. We believe we could push it to 1.55 microns. So that's, I think that's the real answer to your question. That even with the ITO, we think we can push it to 1.55 microns. And boy, there's a periodic table with 100 elements. So binary compounds, there's 10 to the fourth of them. So there's a huge parameter space that we can explore for other materials that potentially work better.
So you can actually shift N2 to any wavelength?
Shift the E and Z wavelength, yeah.
Yeah.
Well, to within reason. Do you remember the answer, Zahir?
Yeah, so it depends on your fabrication, so what pressure, so what do you say?
No, but do you remember the range we can hit?
Oh, so I think you can go from 800 to 2,000 even longer wavelength. So it depends on
800 to 2,000, okay.
2,000 to the very minimum.
Okay.
So in shorter wavelength it's more difficult, longer wavelength is much easier because it depends on what's your oxygen concentration. So
And I-
less doping goes longer. That's more complicated question. That also depends on, so imagine
Oh, yeah, and how you put it down even matters.
Yeah, right.
I mean, the microstructure, the microcrystalline structure changes. It's a mess. Many people said, Robert, don't work with ITO. Or don't try to do quantitative measurements of ITO. It's just, you really don't want to go there.
Any more questions? Okay, if no questions, we thank the speaker one more time.
Okay. Thank you, thank you, thank you. I don't want to speak out of turn, but there might be still food back there.
Yes,
so.
we have coffee and some muffins here. So.